Hi guys, welcome to our next lesson. This is Text and Text 6, chapter 3.6. We're going to be doing these questions here, 1, 3, 6, 7, 11. The topic today is the conjugate roots theorem. And all of these questions are on page, 116. So the conjugate roots theorem is this, well, here's a motivation for it anyway. If I take this quadratic here, z squared plus 2z plus 2, and use the quadratic formula, I'll say minus b plus or minus the square root of b squared minus 4ac all over twice a. What I'll get is minus 2 plus or minus the square root of 4 minus 8 all over 2, which is minus 2 plus or minus root minus 4 over 2, which is minus 2 plus or minus 2i over 2, which means z can be two values. It can be minus 1, dividing top and bottom by 2, minus 1 plus 2i, plus 1i, or minus 1 minus 1i. Okay, so let's look at them again, So minus 1 plus I, or minus 1 minus I. And hopefully you'll spot that these are conjugates of each other. That is, complex conjugates, 1 plus I and minus 1 minus I. Okay, so you've changed the sign here in the middle. And the conjugate roots theorem says that's always true. It says if you have one complex number as a root, then you will also have its conjugate as a root. Okay, now this is only true when coefficients of z squared, z, and the constant term all have to be real numbers. So it's only true when there's no i's cropping up anywhere in the original equation. But that it's also true for any polynomial. Okay, so this is a second order polynomial, but a third order polynomial, something that had z cubed, if it was 3z cubed plus 5z squared plus 2z plus 5 equals 0. For example, that's a third order polynomial, or a fourth order polynomial, which might have a 7z to the 4 or anything like that, fifth order, sixth order. A polynomial is a function in, well, in this case in z, a function in z which has the form a z to the power of n plus b z to the power of n minus 1 plus c z to the power of n minus 2 plus some constant term, okay, which I'm going to call q, okay, where a, b, c to q are all real numbers. Okay, so as long as these numbers in front of the z's are real, for any polynomial, if z is a root, then z bar, the conjugate, is also a root. So let's jump in. So question 1. Question 1 says, show that minus 2 plus 4i is a root of the equation z squared plus 4z plus 20, and write down the second root. Okay, well, to show it's a root, we need to show that if you plug it in, you get 0 as an answer. So here's z squared plus 4z plus 20. There's z, minus 2 plus 4i, and here's z squared. I've done that calculation there. You can do it yourselves as well. So I plug that in. I say z squared plus 4z plus 20 becomes minus 12 minus 16i plus 4 times z is minus 2 plus 4i plus 20. Okay, and if z is a root, then this should all come out as 0. So let's see what we get. Minus 12 minus 16i minus 8 plus 16i plus 20. Okay, well, minus 16i plus 16i, that's 0. Minus 12 minus 8 is minus 20, plus 20 is 0. Therefore, minus 2 plus 4i is a root. And minus 2 minus 4i is also a root by the conjugate roots theorem. Okay, so that's what we're working on. That's our question. Question 3 asks us to form a quadratic equation given a pair of roots in each case. So this relies on you knowing a shortcut that's kind of useful, which is that you can form a quadratic equation from these roots using this shortcut, that it's always going to have the form z squared minus the sum of the roots times z plus the product of the roots. And you can do that anytime, even if the roots are just regular, real roots. So let's see what we get here. That's going to be the sum of the roots is 1 plus 3i plus 1 minus 3i. That's 2. You'll notice that's a real number. That's important. The product of the roots is going to be 1 plus 3i by 1 minus 3i. And the whole motivation for conjugates in the first place was to create real numbers out of complex ones. So this is going to be a real number as well. 1 by 1 is 1. 1 by minus 3i, minus 3i. 3i by 1 is plus 3i. 3i by minus 3i is minus 9i squared. That's going to become 1 plus 9, which is 0. Okay, that bit's 0. Sorry, which is 10. That bit's 0. Minus 9 by minus 1 is plus 9. So the equation we're looking for here is z squared minus the sum of the roots is 2z plus the product of the roots is 10. An alternate method here that we could use is to say, well, by the factor theorem, which is going to become important in just a minute, if, for example, 1 plus 3i is a root, I'll just do this here. If 1 plus 3i is a root, then z minus 1 plus 3i, which is z minus 1 minus 3i, is a factor. Okay, and hopefully you can see the other factor is z minus 1 plus 3i. Okay, so to get to this answer, you could also multiply this by this in an array. Okay, I'm not going to do that here because we have an answer there, but I'll leave you to try that yourselves or see what happens in question 6 with something very similar. Question 3 part 4 gives us the factors plus or minus 5i. Okay, well, using our rule, that's z squared minus the sum of the roots, well, 5i minus 5i, well, actually, plus 5i minus 5i times z, that's going to be 0, plus the product of the roots, 5i times minus 5i. And that's going to be z squared minus 0z, if you like. That's going to be minus 25i squared. So z squared plus 25. Question 6 gives us this cubic polynomial. It says, given that 2 plus 3i is one of the roots, so you know a root now, and if you know one root, according to the conjugate roots theorem, you know 2. So the other root is 2 minus 3i. Find the other 2 roots. So this is a cubic, it has 3 roots. The conjugate roots theorem always gives you pairs of roots. So you know, if you know one, you'll know another. So that's one pair of roots. So we know that 2 plus 3i is a root. Therefore, z bar 2 minus 3i is also a root. Okay, so we know 2 of the roots straight away, and we want to find the third one. So here's how we'll approach this. We'll say, well, z minus 2 minus 3i is a factor. And based on this, z minus 2 plus 3i is a factor. Okay, and that's by the factor theorem, which we met when we did algebra. Okay, if you remember it, it said something like if x equals 2 is a root, then x minus 2 is a factor. That's how we saw it before. Same thing, except now we're subtracting a complex number instead of a real number. And again, we can apply the conjugate roots theorem here because 2, minus 9, 30, and minus 13 are all real numbers. So we know 2 of the factors. If we multiply them together, we're going to get z minus 2 minus 3i multiplied by z minus 2 plus 3i. Let's see what we get. Z squared minus 2z, 3zi minus 2z plus 4 minus 6i minus 3zi plus 6i and minus 9i squared. So you'll notice a few things cancel here, the minus 6 and the plus 6i, minus 3zi plus 3zi. Okay, so what we're left with is z squared minus 4z plus 4 minus 9i squared, which is z squared minus 4z minus plus 4 plus 9 is plus 13. Okay, so that is our quadratic factor of this polynomial here. To find the third factor, divide this into this. Okay, so we'll say z squared minus 4z plus 13 multiplied by something gives us z cubed, 2z cubed minus 9z squared plus 30z minus 13. Well, to get a minus 13 there, we had to have had a minus 1 here. And to get a 2z cubed, we have to have had a 2z up there. So there's your third factor. You can check it all out that it all works out. 2z cubed, that's going to be minus z squared. That's going to be minus 8z squared. So they combine to give us our minus 9z squared. That's good. 2z by 13 is 26z. And minus 1 by minus 4 is plus 4z. You put them together, you get yourself 30z. So you know you got the right answer. So the whole thing can now be written as, well, sorry, we don't even need to rewrite it. We can say 2z minus 1 is a factor. Okay, so let it equal to 0 and solve. And z equals a half is a root. Okay, so our three roots here are z equals 2 plus 3i, z equals 2 minus 3i, and z equals a half. Okay, so our conjugate roots theorem says the complex roots occur in conjugate pairs, and then you've got a third root that will have to be real, because were that third root complex, it would have to have a conjugate pair. Question 7, I'm not actually going to do, I just want to look at an important point in it. Question 7 says, show that 1 plus 2i is a root of this equation. Show also that the conjugate 1 minus 2i is not a root. Explain why. So if you plug this in for z, you're going to get 0, but if you plug this in for z, you don't get 0. So that looks like our conjugate roots theorem is breaking down. But remember, our conjugate roots theorem is only for real coefficients. So because this number here is complex, and this number here is complex, so in terms of your az squared plus bz plus c, well, b is complex and c is complex, the conjugate roots theorem does not apply. Question 11 asks us, form the quadratic equation whose roots are minus 3 plus or minus 2i. Hence form the cubic equation whose roots are minus 3 plus or minus 2i and 2. Okay, so we're looking for a cubic with these three roots. Okay, well the factors are going to be z minus 3 plus 2i, z minus 3 minus 2i, and z minus 2. Okay, so that's just z plus 3 minus 2i, and that's z plus 3 plus 2i. Okay, so let's multiply the complex ones together first. They're going to give us a tidier answer when we work with them together. So z plus 3 minus 2i and z plus 3 plus 2i. So we get z squared, 3z minus 2zi, 3z, 9 minus 6i, 2zi, 6i, and minus 6i squared. Okay, so again, you'll always find this, you get things cancelling with each other. You're left with z squared plus 3z, and 3z is 6z, plus 9 minus 6i squared. So that's going to be z squared plus 6z, 9 plus 6, because that's minus 1 for I squared, is plus 15. So there's our quadratic factor, and then multiply that by our linear factor, we get z minus 2 multiplied by z squared plus 6z plus 15, and we're going to get z cubed minus 2z squared plus 6z squared minus 12z plus 15z and minus 30. So that's going to give us an answer of z cubed plus 4z squared, 15 minus 12 is plus 3z minus 30. Okay, so there's our cubic that has the roots minus 3 plus and minus 2i and 2. Okay, well, for classwork tomorrow on page 116, can we do, please, question 3, I'm going to ask you to finish it off. Question 5, question 7 we looked at, but I'm going to ask you to do in class tomorrow. Question 9, question 12, and question 13, if you get the time. 13 is a bit tricky. Okay, so I'll see you tomorrow. Thank you.